Cycle 2, Lesson 2. In this lesson, we are going to start looking at something called rates of change. And there's a lot of text, a lot of writing in this particular lesson. So in order to save a bit of time, I decided that I was going to pre-fill in a lot of this lesson for us. So I'll read through it. I'll write the odd thing in here, but a lot of the information is already filled in. Anyway, let's go to let's just start at the very beginning. A rate of change, what is it? It's a measure of the change in one quantity, the dependent variable, y, in other words, often, with respect to the change in another quantity, the independent variable. Often we use x for that one. And there's two types of rates of change. We're going to look at both of them today. There's what's called the average rate of change. I'm going to abbreviate that as ARC rather than having to write average rate of change each time, or instantaneous rate of change, likewise abbreviated to IRC. Let's start with the average rate of change. That one's easier. In fact, it's so easy that it's pretty much the exact same as what you've done for slope in grade 9. But we don't do it necessarily just for a straight line. So the average rate of change between 2 points does correspond to the slope, but the slope of the secant between 2 points. And a secant is a line that joins 2 points on a curve. So if that red graph here, this quadratic it appears to be, the red parabola, is our function, if I want to find the average rate of change between point 1, P1, and point 2, P2, I can connect them with a straight line, treat them as if it's a straight line between those 2 points instead of the curve, and get the slope of it. That's what average rate of change does. So really easy to implement, treat it exactly like you're doing slope. So average rate of change is delta y over delta x, which just means change in y over change in x, which then we can use the slope formula for. y2 minus y1 over x2 minus x1. Instantaneous rate of change is, well, I guess before I say what it is, we need to understand what a tangent line is. So a tangent line is actually a line that touches a curve at a single point. So instead of, compare that to a secant line would be like this orange one here on this graph. A tangent line, if I could try and draw one, let's see if I can. A tangent line might be something like this, and it only touches the graph at one point, and now again there's overlap because of the pen thickness, but that's supposed to represent touching that red graph at one point. That would be a tangent line. Now, because it only touches at one point, we can't get the average rate of change for it using the slope formula. We don't have 2 points to put in there, so we have to do something different. One way of thinking about it is that, say I wanted to, let's draw another sketch here. Say I wanted to find the instantaneous rate of change on this parabola here. And I wanted to get the instantaneous rate of change at this point. So again, I know that I could get a tangent line for it, but it's hard to, I guess I could estimate where the tangent line is going to be. But another thing I could do to be more precise for a tangent line is I could consider points on both sides of this tangent line. Say I pick a point equal distance on either side of the tangent line, and then I was to draw a secant through that. That's a pretty close approximation to the tangent line, what the tangent line would look like. But if I wanted to make my approximation better, I could move these points a little closer together and draw a secant through, say, these two, and I would get a better approximation of my tangent line. And I could keep doing that. I could keep moving these points closer and closer to the tangent, to the point I actually want, until the slope between them would actually be a very, very, very close approximation. So that's a way of relating secant line to a tangent. So secant line just between any 2 points, but if I want to get closer to the tangent line, make those points get closer and closer to each other. Let's look at some examples on how we actually use it. So again, average rate of change is the easiest. Let's start with an example of that. New antibacterial spray is tested on a bacterial culture. Table shows the population P of the bacterial culture T minutes after the spray is applied. So you can see down this column here, we've got the different times in minutes. We can see down this column here that we've got the population of bacteria left. So it's killing off the bacteria, and so they are disappearing. And then it's plotted here on the right. Here's a graph of it, right? So you can see, yeah, they're dying off, getting closer and closer to zero after about 8 minutes or so. How can you tell that the average rate of change is negative? By examining, first of all, the table of values. So if we just look at the table of values, we can tell that the average rate of change is going to be negative because as t is going up, getting bigger, the rate of change, the p, the population, is getting smaller, right? So as t increases, p is getting smaller, it's decreasing. From the graph, we can tell that the rate of change is going to be negative because the graph is going downwards as we move from left to right. If I pick any 2 points along here, randomly, the second one, the one on the right, is always going to be lower than the one on the left, so it's always going to have a negative slope involved. And that's not just for those 2 points, but for any 2 points that I choose. And so a negative slope is going to correspond to a negative rate of change. If I want to determine the average rate of change of the number of bacteria over the entire period, this is where our slope formula is going to come in. So the entire period starts at time 0 and ends at time 7, and then with the corresponding populations. So, we've got x1, y1, x2, y2. Put them in the appropriate place into the slope formula, as you can see I've already done. And we end up with a slope, an average rate of change, ARC, of negative 109. So what does that tell us? It means that on average, the bacteria are decreasing by 109 per minute. Compare the average rate of change in the number of bacteria for the first 3 minutes and the last 3 minutes. So these are 2 different questions. So for the first 3 minutes, we're going from time 0 to time 3. And again, the corresponding populations give us x1, y1, x2, y2. So 737 minus 800 over 3 minus 0 gives us an average rate of change of negative 21 bacteria per minute. So compare that to the 109 from the previous one. They're not killing that many bacteria as at the beginning as the average rate of change overall is. And then if we compare that to the last 3 minutes, that would be comparing the points that go from minute 4 to minute 7, and when I get the slope of that, I end up with negative 205 bacteria per minute, so they're dying off much faster as time goes on. How can you tell that this situation involves a non-constant rate of change by examining various things like the table of values? Well, I can tell if I was to do the first differences on the table of values, I would see that they're not constant. If they're constant, it's linear, but if they're not, so it's a non-constant rate of change. The graph, again, would be linear if it was constant. It's not, it's a curve. The average rate of change if I compare all these different average rate of change, negative 109, negative 21, negative 205, they're all different. If this was constant, I would have got the same answer for all of them. So that's an average rate of change from a table in a graph. If I'm given an equation, well, we can still work with this. A football is kicked into the air such that the height h in meters after t seconds can be modeled by the function h at t equals negative 4.9 t squared plus 14t plus 1. Determine the average rate of change of the height of the ball for each time interval. So I said that the x values were given, but really it's the t values. So the t values are given. So what does this mean here? Square bracket 0, 0.5 square bracket. That's a way of giving an interval. So square brackets are giving us an interval. It's saying go from 0 on the one end to 0.5 on the other. So I want the time interval that begins at 0 seconds and ends at 0.5 seconds. Being average rate of change, I'm still going to use the slope formula. And another way of looking at this is they're giving me x1 and x2. They're giving me both x values, or t1 and t2. I guess I should be consistent with that. So t1 and t2, they're like my x1, x2. But I need the height to go along with it, the y values. So I'm going to get that by plugging it into the equation. So I didn't show the work for doing this, but I'll show it now, at least for one of them. Well, actually, for the first one, let's do it for the whole thing. I guess I need to open my calculator. If I put 0 into the equation, actually, there's no point in using the calculator for this part. If I put 0 into this equation for t, this term disappears, and all I'm left with is 1. So the height at 0 seconds is 1, which is where this comes into play. Okay? If I put 0.5 into this equation, then what happens is, this is where I'll use the calculator, and I'll go negative 4.9 times 0.5 squared plus 14 times 0.5 plus 1. So we just plug it in, we get our y value, and I think I made a mistake here, or did I? Nope, I just didn't hit equals. I got 6.775. So my height is 6.775, which you can see I wrote down the answer for it here. I just didn't have room to show all my calculations. So that's like my y1 and y2, respectively. So those are what go into my slope formula, right? y2 minus y1 over x2 minus x1, and it turns out that the average rate of change is 11.6 meters per second. So it's going up, this football is rising into the air at an average rate of change at 11.6 meters per second for the first half second. Once we get to time 2 seconds to 2.5 seconds, again, I calculated the y values that go along with it. So here's y1, here's y2, plug them into the equation, the slope formula, and work it out. And for this one, we got negative 8.1 meters per second. So in other words, we've passed the peak of the ball. The ball must be falling back to Earth at least by 2.5 seconds, and it's changing at a rate of negative 8.1 meters per second. It's falling now at a rate of 8.1 meters per second. Consider the graph. Here's the same equation. They've drawn a couple secants, one from A to B and another one from C to D. Describe the relationship between the values in part A, the secant lines in the graph. Let's just compare the two secant lines, because that's what I've got written down here. So part secant line AB, we can see it's got a steep slope, steeper than CD is. It's going up as I read it from left to right. Going from A to B, we're definitely going upwards. And the average rate of change, it is the average rate of change for 0 to 5 seconds. For CD, that is less steep, and we can see it's decreasing as we read it from left to right, like a negative slope, and it corresponds to the average rate of change from 2 to 2.5 seconds, so that would be the negative 0.81 again. Now, instantaneous rate of change. As stated before, we can do that by considering a tangent line. So the example we have here is a graph showing an approximate distance traveled by a parachutist in the first 5 seconds after jumping out of a helicopter. How fast was the parachutist traveling 2 seconds after jumping out of the helicopter? So this is a specific point. So this isn't a range. It didn't say from 2 to 3 seconds or something like that. We want to know at the exactly 2 seconds after jumping out of the helicopter, what was the speed, the rate of change. Speed is just a rate of change at that point. So it's the rise over the run. So we still can use the tangent line. We can get the slope of a tangent line, but in this case, I've already drawn it on here again. So this red line is my best guess at what a tangent line would be at 2 seconds, right? 2 seconds is this point right here. And again, you can see I put these little blue dots on, which would be a secant line that would be close to 2 seconds. And it's similar. I would get a similar slope. But I drew my tangent line, and then once I've drawn the tangent line, then I ignore the actual graph and I focus strictly on the tangent line, and I go, okay, what's the run? There's my run, 2 units. I just picked another point, and the other point I picked was 460, and so the rise was 40, the run was 60, so rise over run gives me my slope. So I don't even need to use the slope formula, not the one that's y2 minus y1 over x2 minus x1, just rise over run also gives me slope. So if we've traveled 40 meters in 2 seconds, then it must be 20 meters per second. And again, we're just using that line because it estimates the speed at that moment. If I want to estimate the parachutist's velocity at 2 seconds using a table of values, then I can use a couple of methods. So these are 2 separate methods. We've got the preceding and following interval method, or we can use the centered interval method. We don't need to use both of them. They get us to the same place. So let's look at the preceding following interval one. If we get the average rate of change for a small secant just before 2 seconds, then we also get the average rate of change for a small interval just after 2 seconds, and then average those two together, then that'll give us a good estimation of the instantaneous rate of change exactly at 2 seconds. So I took a very small interval. So here's our table of values. In fact, we'll use that. So we want to find the instantaneous rate of change at 2 seconds. So right here. Remember, this 20 is not the instantaneous rate of change. It's actually just the distance. It's too bad that the distance traveled was 20, which was also our instantaneous rate of change, because that adds a little bit of confusion, but I can't change that. Anyway, so this is the distance traveled. So at 2 seconds, the parachutist has traveled 20 meters from the airplane. At 1.5 seconds, the parachutist has traveled 11.25 meters from the airplane. So I can get the average rate of change between these 2 points. And so that's exactly what I'm doing right here. It turns out the average rate of change for that half-second interval is 17.5 meters per second. If I do the same thing for a half second after the time I want, so 2.5 seconds, and then compare that to the 2 seconds, then I can get my average rate of change as 22.5 meters per second. So the parachute is picking up speed. As they drop, gravity kicks in, and so at 1.5 to 2 seconds, they're going 17.5 meters per second. At 2 to 2.5 seconds, they're going at 22.5 meters per second. So they've increased by 5 meters per second over that time period. If I want to find out then what the instantaneous rate of change is, what I do is I then average those two. So I'm going to average this and this, put it in here, so add them together, divide by 2, and I get 20 meters per second. So that is the average rate of change, 20 meters per second. Centered interval, if I move on to this part here, uses points on either side. So instead of doing two intervals, two average rate of change and then averaging them, I can just take an interval which is centered around the one I'm looking for. So again, if I'm looking for at 2 seconds, maybe I'll just look at, okay, I'll take a half second before that and a half second after that, get the average rate of change between those two intervals, and that should give me a pretty good ballpark as well. So then I use the slope formula again, and I got 20 meters per second overall in that one. They won't always give you the exact same answer for every one, but in this case they did, and that's good. But just don't expect that that's always going to be the case. Okay, you can use either one. Obviously the centered interval seems to be a little bit less work. There's one last way that we can do an instantaneous rate of change, and that's using something called the difference quotient. We can only use that on an equation. So if we've got this equation for the sorry, there's a tractor going by my window. All right, if we've got an equation, then we can use what's called a difference quotient, and it's actually the most accurate way of getting our instantaneous rate of change. And so what we do is we use a really, really tiny interval, but this time, because we've got an equation, we can pick any interval we want. So usually we use an interval of like 1/100th of a unit or 1,000th of a unit. I use 1,000th of a unit. So I use h equals 0.001. That's 1/1000th of a unit. And I add that to whatever point I'm trying to find, and I subtract that from whatever point I'm trying to find. And then again, I go back to my slope formula. So if I go 1,000th of a unit before the 2 seconds, we're still finding it at 2 seconds. I subtract 1,000th of a unit from that, like I'm doing right here. 2 minus 1/1000th of a unit gives me 1.999. If I do it again and add 1/1000th of a unit to that, I get 2.001. Those are my two x values, again, for my slope formula. Call this x1, call this x2, or t1, t2, whatever. Plug those into the equation, plug those into 5t squared, and when I do that, I'm going to get a y value, an output of 19.9800, etc. For the first one, I get an output of 20.00200005 for the 2.001. And again, those are my y1 and y2 respectively. Those go into the formula. And so this one goes here, this one goes over here, this one goes here, this one goes over here. You do the slope formula, work it all out. I got, again, 20 meters per second. You'll notice, though, one last thing before I stop letting you listen to sounds of heavy machinery going by. The last thing I want to point out is that I used a lot of decimal places for the difference quotient. whatever, use as many decimal places as are available to you when you're doing that. That's why I wrote down 6 decimal places for my y values, because that was available to me. The more decimal places you can use for the difference quotient, the more accurate it's going to be. And the reason you need so many decimal places is because you're using such a small interval. Since I'm only using 1/1000th of a unit for my difference here, it's going to round it too much if I don't carry a lot of decimal places.